Good day, everyone. I am Reina Marie de Bisaya, and I'm going to discuss the 5 selected examples from different topics. First, we have differential calculus of functions of more than one variable. The function f of x and y is differentiable at the point a and b if and only if the surface z is equals to f of x and y has a non-vertical tangent plane at a and b. Therefore, if the surface of f of x and y at point a and b is smooth and not containing cusps, edges, breaks, etc., then it is differentiable at that point. In the previous lesson, partial differentiation was introduced for the case where only one variable changes at a time, the other variables being kept constant. In practice, variables may all be changing at the same time. If z is equals to f of u, v, w, and so on, then the total differential dz is given by the sum of the separate partial differentials of z. In this diagram, we see two kinds of changes, delta x and delta y. These are the actual changes in x and y. Think of them as measurable differences you could record. dx and dy, these are the differentials of x and y, the tiny changes we use in calculus. For independent variables like x and y, we simply set delta x, dx is equals to delta x, and dy is equals to delta y. The dz or the total differential, this tells us how z changes when both x and y change a little. It is calculated using the partial derivatives. dz is equals to partial z over partial x times dx plus partial z over partial y times dy. In simpler notation, dz equals f sub x times dx plus f sub y times dy. Here we have the formal definition of differentiability for a function z is equals to f of x and y. It tells us exactly what it means for a function to be differentiable at a point. Differentiability means the actual change in z, called delta z, can be broken into two parts. First, a linear part, like the total differential dz. Second, a vanishing error part that goes to zero as changes get small. F sub x at x sub 0, y sub 0 times delta x plus f sub y at x sub 0, y sub 0 times delta y. This is exactly the total differential dz we saw earlier. It's the linear approximation to the change. Next, we have the error terms epsilon 1 times delta x plus epsilon 2 times delta y. These are the errors in our linear approximation. Epsilon 1 and epsilon 2 are functions that go to 0 as delta x and delta y go to 0. As delta x, delta y approaches to 0 and 0, this means that as the changes get smaller and smaller, the error disappears, and our linear approximation dz becomes exactly equal to the actual change delta y, delta z in the limit. A function is differentiable in a region R if it is differentiable at every point on that region. For example 1, find the total differential of the function. F of x and y is equals to 2 times x raised to 4 times y minus 8 times x squared times y cubed. So solution, z is equals to 2 times x raised to 4 times y minus 8 times x squared times y cubed. First, we are going to state the formula for determining the total differential with respect to the given function. So dz is equals to the partial z over partial x times dx plus the partial z over partial y times dy. Determine the partial z over partial x and partial z over partial y. Then simplify. Z is equals to 2 times x raised to 4 times y minus 8 times x squared times y cubed. For partial z over partial x, so it will become the quantity of 8 times x cubed times y plus 2 times x raised to 4 times 0 minus the quantity of 16x times y cubed plus 8 times x squared times 0. So 8 times x cubed times y plus 2 times x raised to 4 times 0 is equals to 8 times x cubed times y plus 0. And then 16x times y cubed plus 8 times x squared times 0 is equals to 16 times x times y cubed plus 0. So the partial z over partial x is equals to 8 times x cubed times y minus 16 times x times y cubed. For our partial z over partial y, we have 0 times y plus 2 times x raised to 4 times 1 minus the quantity of 0 times y cubed plus 8 times x squared times 3 times y squared. And then simplify, we have 0 plus 2 times x raised to 4 minus the quantity of 0 plus 24 times x squared times y squared. And final, partial z over partial y is equals to 2 times x raised to 4 minus 24 times x squared times y squared. Next, substitute the values of partial z over partial x and partial z over partial y in the formula, then simplify. So we have dz is equals to the quantity of 8 times x cubed times y minus 16 times x times y cubed dx plus the quantity of 2 times x raised to 4 minus 24 times x squared times y squared dy. Then factor. So we have the final dz is equals to 8 times x times y times the quantity of x squared minus 2 times y squared dx plus 2 times x squared times the quantity of x squared minus 12y squared times dy. Next, we have the double integral. This is the definition of a double integral over a region R. The double integral over R of the function f of x and y dA. The double integral symbol tells us we're integrating over two dimensions. The R below indicates the region in the xy plane we're integrating over. dA is the area element representing a tiny piece of area. The limit as m and n go to the infinity of the double integral of the double sum from I equals to 1 to n and j equals 1 to m of f evaluated at x sub I, y sub I times delta A. Here's an important fact about double integrals. If f of x and y can be written as g of x times h of y, that is, the function separates into an x part and a y part. And if we are integrating over a rectangle R equals a and b times c and d, then the double integral splits into a product of two single integrals. The double integral over R of f of x and y dA equals the double integral over R of g of x h of y dA, which equals the integral from a to b of g of x dx times the integral from c to d h of y dy. Evaluate the double integral over R times x cosine squared y dA. R is equals to negative 2 and 3 and 0 and pi halves. Since the integrand is x times cosine squared y, we can use the separability fact. Applying it, we can get the double integral equals the integral from negative 2 to 3 of x dx times the integral from 0 to pi halves of cosine squared y dy. Integrate with respect to x, we get 1 half times x squared, and then evaluate from negative 2 to 3, we get 5 halves. The second integral, we are going to use the identity cosine squared y equals 1 half times 1 plus cosine of 2y. Then, we're going to integrate, and the integral of y is 1, and the integral of cosine 1 is 1 half sine 2y. Evaluating the second integral, we get pi over 4. Multiplying the results, pi halves times pi over 4 is equals to 5 pi over 8. This is the triple integral. This is the definition of a triple integral over a solid region Q. It extends the idea of integration from area to volume. The triple integral over Q of f of x, y, and z dv. The triple integral symbol tells us we are integrating over 3 dimensions. Q is the solid region in 3D space. dv is the volume element, a tiny piece of volume. The limit as the norm of delta goes to 0 of the sum from I equals to 1 to n of f evaluated at x sub I, y sub I, z sub I times delta v sub I. We have the properties of tripole integral. The triple integral over q of a constant times f of x, y, and z dv equals the constant times the triple integral of f of x, y, and z dv. Constant can be factored out of the integral. Like if you are integrating density times volume and density is constant, pull it outside. Next property, the sum and difference rule. The triple integral of f plus or minus g equals the triple integral of f plus or minus the triple integral of g. So we can split the integral of a sum into separate integrals. It is useful when f and g are easier to integrate separately. And the last property, we have additivity over regions. The triple integral over q equals the triple integral over q sub 1 plus the triple integral over q sub 2 if q is split into two non-overlapping subregions. If a solid q can be divided into two parts, we can integrate over each part separately and add the results. In the properties, q is the union of two non-overlapping solid subregions, q sub 1 and q sub 2. If the solid region q is simple, then the triple integral of f of x, y, and z dv can be evaluated with an iterated integral using one of the 6 possible orders of integration listed below. So we have dx times dy times dz, and dy, dx, and dz, and also dz times dx, dy. Then dx, dz, and dy, dy, dz, and dx, and last, dz, dy, and dx. Evaluate the triple integral over rectangular regions. R equals the set of all points x, y, and z such that x is between 0 and 2, y is between negative 2 and 3, and z is between 0 and 1. The triple integral over r of x squared, y squared, z squared dv. The triple integral from 0 to 1, 0 to 2, and 0 to 3 of x squared, y squared, z squared with respect to z, then x, then y. The integral is rewritten by grouping the inner integral with respect to z. Since x squared and y squared are constant with respect to z, they are factored outside the z integral. The integral of z squared is z cubed over 3, evaluated from 0 to 3. Substituting the limits gives 3 cubed over 3. Put 1/3 outside, then evaluate z cubed from 0 to 3. So we have now 27. 1/3 multiplied by 27 is 9. So the integral from 0 to 2 and 0 to 1 of 9x squared y squared dx dy. Next, we are going to integrate with respect to x. Since 9y squared does not depend on x, we factor it out of the inner integral. The integral of x squared is x cubed over 3 evaluated from 0 to 2. The integral from 0 to 1 of 9y squared times x cubed over 3 evaluated from 0 to 2 with respect to y. Substitute the upper and lower limits, 2 cubed over 3 minus 0 cubed over 3. Simplify inside the parentheses, we have 2 cubed is 8, so the expression becomes 8 over 3. Multiplying the constants, 9 times 8 over 3 equals 24 over 3. And then simplify, we have 72 over 3 simplifies to 24. The integral of y squared is y cubed over 3 evaluated from 0 to 1 and multiplied by 24. Evaluating the limits gives 1 over 3 and 24 times 1/3 equals 8. Therefore, the integral over r of x squared y squared z squared dv is equals to 8. Next, the separation of variables. One of the most straightforward methods for solving differential equations is the separation of variables technique. This method allows us to break down complex equations into simpler components by isolating variables, making it easier to integrate and find solutions. So we are solving a first-order differential equation using the separation of variables. That means we want to get all y terms on one side and all x terms on the other. 4 minus x times y prime equals y squared. So we write it as 4 minus x times dy over dx equals y squared. We want to separate y and x. Multiply both sides by dx and divide both sides by y squared and the quantity of 4 minus x carefully. So dy over y squared equals dx over 4 minus x. Now, all y terms are on the left with dy and all x terms are on the right with dx. Then, the equation is separated. Y to the negative 2 dy equals 4 minus x to the negative 1 dx. We've already separated variables, y terms with dy on the left, x terms with dx on the right. Integral y to the negative 2 dy equals integrate 4 minus x to the negative 1 dx. Integral of y to the negative 2 is negative y to the negative 1 or negative 1 over y. Integral of 1 over 4 minus x is negative natural log of absolute 4 minus x. So we have negative 1 over y is equals to negative the natural log of the absolute value of 4 minus x plus c. So multiply through by negative 1. Multiply both sides by negative 1 to clean up the signs. C is an arbitrary constant, so negative c is still just a constant, which we can call negative c. Y equals 1 over the natural log of absolute 4 minus x minus c. Solve the equation dx plus e raised to 3x dy equals 0. Solution, we're going to rewrite the equation. This is a first-order separable differential equation. It's written in differential form, which is a perfect for separation. So rewriting it, dx plus e raised to 3x dy equals 0. Dx equals negative e raised to 3x dy. E to the negative 3x dx equals negative dy. We divided both sides by e raised to 3x to get all x terms with dx and all y terms with dy. Now, the variables are separated. The integral of e raised to the negative 3x dx is equals to negative of the integral of dy. The integral of e raised to negative 3x is negative 1/3 e raised to negative 3x plus c sub 1. And our right side, negative integral of dy is negative y. Now we are going to combine the constants. Negative 1/3 e raised to the negative 3x equals negative y plus c. And now solve for y. Y equals 1/3 e raised to the negative 3x plus c. Therefore, the general solution of the given problem is y equals 1/3 e raised to negative 3x plus c. That's all for today. I hope you learned something from me. Thank you for watching and God bless us all.